Hello everyone, welcome to my RubyKaigi talk. Today I'm going to talk about mruby-rr, Time Traveling Debugger for mruby using RR. So about me, I'm John Lin. I'm from Taiwan, and my Twitter handle is JohnLinVC. I'm a senior solution architect at West Pharmaceutical. And today's agenda, first I'll introduce the use case of mruby-rr, and then talk about the internals of mruby and RR, mruby-rr and RR. And then I'll show the benchmarks and then talk about the future works. So there's some bugs that are hard to reproduce in our common ML programs, right? So the most notorious one is the race condition. Basically, you have multiple threads or fibers that are competing with each other for some variables or for some data. And then this kind of bug is hard to reproduce because the data, the timing is critical. So it's hard to reproduce the timing of the thread conditions. And the second one is UI bugs. So basically you need specific user inputs, like clicking specific buttons or a specific position in a specific sequences. So this kind of bugs are also hard to reproduce. And the third one is random related. So if you are using any random generated data, like random number, this kind of bugs are pretty hard to reproduce because you cannot easily reproduce all this random data. So this is pretty related to current topic like cryptographic. And then last one is time related, especially if it's related to time.now, right? Because when time passed, you couldn't go back. So here is a pretty simple time-related bug. So we have a variable a with current time, and then we print it, and we do some process of it, and reassign it back to a. So when we execute it, the first time we execute it, we think the 2 times printed are exactly the same, which is our expected result. And then the next one, the next time we run it, because we do the rounding in our code, right? So the 2 times are different, and this is not our expected results. So using the stock, the official mrdb debugger, how can we trace this issue? So first we invoke mrdb with mrdb t.rb. Then we will try to break at line 2 of t.rb. The reason to break it 2, because if we break it 1, the variable a hasn't get a value yet. So we have to break at the beginning of line 2. And then we allow the program to continue execution. And then we try to evaluate a. So we try to get the value of a. We can see it's 13851. And then we try to break at line 4. And then we do continue. So here we'll try to get the value that's modified of the modified a using eval. So we can see here is 13852, which is different from 13851. But the problem is, after we reach in line 4, there's no way we can go back to line 1, right? Because there's no time machine. So how should we do? Well, all we have to do is find a time machine, right? So there exists time machines in programming world. This one is called Time Traveling Debugger. So what is Time Traveling Debug? So time traveling debugging is a process of stepping back in time through source code to understand what is happening during execution of a computer program. This is definition on Wikipedia. So basically, a time traveling debugger have all features that usual debugger have, such as break and continue and eval. But it can do extra things. It can do reverse execution. So we can do like reverse next or reverse continue. So here we are, today's topic, mruby-rr. So mruby-rr is an experimental mruby time traveling debugger that uses RR as backend. So I write mruby-rr as a proof of concept, try to show that it's possible to do time traveling debugging in Ruby. And mruby-rr uses record and replay to provide navigation and inspection to programs. And it works on Intel CPU and Linux. So how do we trace that program using mruby-rr? So first we record that program using record and pass it the arguments and a script file. So we will run the program as usual. And then you'll do all the output. And you also output the trace data. And then next we run replay. So after we start the mruby-rr, and then we can tell it to break at the second line of t.rb. So we create a breakpoint. And then just like we did in mrdb, we tell it to continue execution. So you will stop at the second line of t.rb. And then we do an eval. So we will print out the value of variable a. So it's 13105. And then we want to get the modified value of a, right? So we break at the fourth line of t.rb. And then we do a continue. And you'll stop at the line 4. And then we'll just try to get the value of a. So the a is the modified value. So what's special here is that in mruby-rr, after we go to line 4, we can do a reverse continue. So what reverse continue do is that you'll reverse the execution direction. So you'll go back in reverse order until it hits another breakpoint, which is the breakpoint 1. And then here we can evaluate the value a again, so we can get its old value. So we can see here is that after we go back in time, we can get the old value of a, which is the value we really want to have, really want to inspect. Another feature is that it can start over because it's a recorded trace data. So we can start from scratch just by telling it to start. So it will restart from the beginning. And then we do continue. So we'll stop at the first breakpoint in line 2. And here we can see that it's having the exact same data as last execution. So no matter how hard the bug is, you can always faithfully reproduce the last recorded running states. So now we have a time machine for mruby. So how do we get the time machine? First, you have to install mruby-rr. So you have a hard dependency RR. We'll talk about it later. And the first step you'll need is to add mruby-rr to your build config of mruby, and then enable debugging support. So you first add enable debug, and then enable the debug hook by adding mrb enable debug hook to cc.defies. And then add the mruby-rr repo to your gem. We need that because we need to set up the debug hook to mruby itself. And then you build mruby from source. Then you clone the mruby repo so you can have the debugger binary. So the commands of mruby-rr are record and replay. So for record, you tell it to record and give it the script file name and then the argument it needs. And for replay, you can give it the optional trace directory. If you don't give it a trace directory, you'll use the latest trace performed on this computer. So the current features on mruby-rr are The first one is obviously break, so you can set breakpoint at specific file and a specific line. And the next one is next. So next will go to next line in the same file and stop there. And continue is to continue execution until hitting another breakpoint. And eval is that you'll evaluate the expression, the Ruby expression inside mruby and print the output. And the next are the time traveling commands. So the first one is reverse continue. So reverse continue is like continue but in backwards. So you'll go back in time until hitting another breakpoint. And reverse next is the reverse version of next. So you go back one line. And start is that you'll restart the program from scratch, but you'll keep all the states from the recorded data. So you will not get a new time. You'll get the time as you run the record command. So this is helping you find where you are now. So how does mruby-rr works? So here is a diagram. So first, mruby-rr will start an RR process, and the RR process will start an mruby process. And mruby-rr will store execution info like the breakpoint list inside itself. So here we need to talk about RR. What is RR? It's a fast time traveling debugger by Mozilla. Fast is a very important feature for RR because in the past, time traveling debugger tend to be pretty slow. And RR is one of the fastest one existing now. And it's a direct replacement of GDB. And just like GDB, it's language agnostic, but just like GDB, it supports C and C++ best. So it doesn't have any built-in features for other languages yet. And it works on real application. So for example, it works for Firefox and Chrome and QEMU, and some of the developer of these applications use it to debug real-world bugs. So let's see how a program executes a normal program. So here is a very simple program. Int a equal 1 + 1, and then print the value of a out. So here we have a very important concept is that any program they want to do any real impact in the real world, you have to do it through system calls. So that you can get the input data from operating system and then output data to other devices like screen or files. These are all made possible by system calls. So the first thing the program execution is that so you will do 1 + 1 and you assign it to A. And this one doesn't have any system calls, so we'll go directly to the CPU. And the second line is the printf. Printf is actually a system code, so we will do the pass the system code to the kernel. And after the kernel executes that system code, you'll return to your program. So that's how the normal program communicates with real world. So the only thing we need to record are the system calls. So we only need to record the timing of all these system calls and context switches. So let's see how RR record program execution. So first, RR will tell the kernel to start intercepting system calls. It's using a ptrace to do the interception. And then the program will do a normal execution, normal instruction without system call. So this one will go directly to the CPU. And then the next one is the program can do a system call, and you will call the kernel to do the printf. But after kernel receives that system call, it will not execute it directly. You'll notify R first. So it will notify R that you get a system call. And R will store the parameter to a trace file. And then the kernel will do the actual system call, and then call R again. After that, R will store the result of the system code to a trace file. So this is how RR gather all the trace data from the kernel. So it's using ptrace to get all the system code parameter and results. But how about timing? So the system code timing is very important because we need the timings of the system code's return time to reconstruct the whole running procedures of a program. But most CPU performance counters are not deterministic. Things like patch fault, basically you try to get access memory and it doesn't exist in the memory yet. That one will retry that command again. You try all these instructions again, and you'll all get they will all make the performance counter invalid, not accurate, not invalid. But Intel CPU has a special performance counter that is deterministic. That means it's not affected by page faults or other things. It's called retired conditional branches, RCB, which means how many conditional branches have been done. And R use RCB and the general register, all the register of the CPU, including the program counter. And then you also gather the stack frame data. So you combine all these three data to identify the execution timing. So we can reproduce the timing when we play. So R has some limitations. The first one is that since it's using an Intel specific performance counter, it only runs on Intel CPUs. And then since it's using ptrace, it's only available on Linux. And another one is that it's forcing all thread and process to run on a single core. So that if your program are multi-core like Mac, you're gonna be slowed down quite a lot. Otherwise, the performance is quite good. So let's go back to mruby-rr. So how mruby-rr communicates with RR is going through the GDB-MI interface. So what is a GDB-MI interface? It's a text-based machine interface of GDB. And it's designed for ID and automation tools. So it's using stdin for command input. And you'll do the output from standard output. That part is the same for normal GDB, right? But the different part is the output part is formatted and it's easier to parse for machine or scripts. And so the user interface of mruby-rr, first we'll start RR in MI mode using popen. And then mruby-rr will use readline to get user inputs. And you'll parse the user input and issue the corresponding MI commands to RR. And read output of RR asynchronously in another thread. And mutate internal states based on the RR output. So you'll do like get breakpoint number, some stuff like that based on the RR output. The way we try to set breakpoint is utilizing mruby's code fetch hook. Code fetch hook can be enabled with cc defines, and you add mrb enable debug hook, and you can enable the code fetch hook. So what is code fetch hook? Code fetch hook is just like Ruby's tracepoint API. So whenever mruby execute an instruction, you'll call the code fetch hook and provide the current program counter and the current state of mruby, and along with all the registers. So how do we do a break? So in the code fetch hook, we get the current file name and the line number from PC and irrep. And we call an empty function mrr hook with the file name and line number. And we set the conditional breakpoint on that hook with the target file and line number as a condition. So we basically ask mrr to insert breakpoint at the hook with specific conditions we provided. But there are some issues. The main issue is that unlike tracepoint, call-fetch hook invokes on every instructions instead of every line. So for example, put x will have more than one instructions. So the conditional breakpoint that rely on only file and line number will break more than once when there's more than one instruction at a line. So like put x will break like 2 or 3 times. So the current temporary solution is that we'll temporarily disable the breakpoint when we try to continue. And after we hit the next breakpoint, we'll enable them again. So next is continue and reverse continue. This is the easier one. We just proxy all of them to RR. And then for list, this one is implemented without RR. So we just format and print the code using the current file and line number information. And next and reverse next, this one is a little bit hack. So I set the temporary breakpoint on next or previous line. And then we do a continue new or reverse continue. And you'll hit at next or previous line, right? And because it's a temporary breakpoint, you'll automatically delete itself. So we have the same effect as next and reverse next. And eval, this one actually I borrow some of the eval code from mrdb. And I rename it and link it to mruby. And then how we do is call the eval function using print in RR. So we'll do the data evaluate expression and pass it the eval code function name along with the Ruby expression. So that it will do the eval by calling the command print function. And then we get the output from RR and we display it. So next is the benchmarks. So there's a built-in benchmark benchmark script in mruby. This one is AO render. I set the parameter to 16 for WNH. So for an ordinary mruby with hook, it's around 3 seconds. And for recording, mruby-rr recording takes like 5 seconds. So it's around 1.6 times slower. And for replay, it's around the same time as normal mruby. So the replay speed is pretty fast. Another example is the Fibonacci, also inside mruby, and I set into 30. So for normal mruby, it took around 5 seconds. And for record using mruby-rr, it takes around 8 seconds. So it's 1.6 times. And for replay, it's around the same as original mruby. So it's pretty fast. And next one we care about is a trace file. So for Fibonacci, it's around 40K. And for L render, it's 56K. But I will need to do more tests on system heavy programs, like programs with a lot of I/O, such as HTTP server. So there's current some issues of mruby-rr. The first one is it cannot recreate an alternative universe, so all side effects in eval are erased. And next one is a lot of features are not implemented yet. And then the replay speed reduced significantly when there's breakpoint enabled. So for future work, the first one is complete the full implementation, and I'm aiming to have as much feature as bybug. And then I want to speed up replace with breakpoints. And then maybe I want to try remove the call fetch hook so that we can do debugging without mruby gems, but I'm not sure about this one. And then the next, maybe the most interesting one is probably make the ruby-rr. So takeaways are RR made time traveling debugger being easier, and it's possible to do time traveling debugging on mruby or Ruby. Thank you for listening. So mruby-rr is available at GitHub, and feel free to reach me on Twitter for questions, and my Twitter handle is JohnLinVC. Thanks everyone. Bye.